So at the end of that Ant LED video a while back, I made a little tweak at the end of the code, and I released a video the next week about the uint8 variable type definitions that I was using in that video. And I figured now might be a good time to have like a little binary crash course, or talk a little bit more about variable types and what they actually mean. I mentioned at the end of that Ant LED video, I work on robots now a lot, and a part of that is training people how to use robots. A really common problem that we have with a lot of people would get overflow errors, variable overflow errors. And some people will set up counters to tell the robot how often to go to the cleaning station. And they'll use a byte variable type in their robot controllers and forget to reset that byte variable back to 0 after we go to the cleaning station. So eventually it'll overflow that byte variable. And I figured we'll talk a little bit about what that means basically, and what our variable type definitions mean. So, I didn't have a marker board, but I figured, hey, I've got this nice white glass table, so we're going to write on some furniture today. I usually start off with just a little kindergarten, I don't know, go back to middle school basically, talking about how the decimal number system works. So, say you have the number 101. Hopefully you can see that. If this doesn't work, I'll go and draw on my iPad. I use Adobe Fresco for all my little, like, drawings and stuff that I put on my videos, but I don't know. This might be a bad idea with all the glare and stuff, but we'll see where we can get. Anyway, if you look at the number 101 in decimal, if you remember back from like middle school, each of these digits has a place value. We call this like the ones place, the tens place, and the hundreds place, right? Remember all that from middle school? So yeah, the ones, the tens, the hundreds. Well, what do these place values actually mean? Well, what we're taking is whatever number's in this place value, we're taking that number, in this case it's a 1, times 10 to the power of 0. And if you remember, I don't know, this is probably high school math, but anything to the power of 0 equals 1. So 10 to the power of 0 equals 1. So whatever digit that we have in our first place value of this number, we take that, which is 1 in this case. 1 times 1 equals 1. Cool. You with me so far? Alright, so take the tens place number and do the same thing. Well, we're taking 0 times 10 to the power of 1, because we're in our next place value. So this is to the power of 0, to the power of 1, to the power of 2, etc., etc. So 0 times 10 to the power of 1, if you remember, 10, anything to the power of 1 is the same thing. So 10 to the power of 1 is 10. Well, 0 times anything equals 0. So our tens place equals 0, which we already know. This is all kind of stupid stuff that you probably don't think about or haven't thought about for a very long time, but this is the way our decimal number system actually works. We're taking each place value times 10 to whatever power that place value holds. So 0 times 10 to the power of 1 equals 0. Alright, let's do our last one real quick. 1 times 10, we're in our third place value now, so we're times 10 to the power of 2. 10 to the power of 2 is 100. And we have 1 times 10 to the power of 2, which is 100, equals 100. Alright, what the heck does all this have to do with our original decimal number that we wrote down up here, 101? Well, if we take this number, plus this number, plus this number, we end up with 100 plus 0 plus 1 equals 101. This might seem really stupid so far, but stick with me for a minute because we're going to talk about binary. Basically, any alternative number system, if you've never, most people know what binary is, the language that computers use. So what does all that power of 10 nonsense have to do with binary? Well, say we're thinking about the same number, 101, but this is now, we're calling this a binary number. Okay? What that means is that each of these place values, the ones place, tens place, and hundreds place, instead of to the power of 10, we're taking all these to the power of 2 now. So we work the same way as we did before. We take this digit, which there's a 1 right there right now. We take 1 times 2 to the power of 0. Well, 2 to the power of 0, remember, anything to the power of 0 is always 1 for some reason. Anyway, so 2 to the power of 0 is 1, so 1 times 1 equals 1. So that's the value we have from that place value. Well, now we're on our next place value. 0 times 2 to the power of 1, since we're on our next place value. Well, 2 to the power of 1 equals 2, and 0 times anything equals 0. Follow so far? So let's go and look at this last one. 1 times 2 to the power of 2. 2 times 2 to the power of 2 is 4, and 1 times 4 equals 4. So, if we do the same thing we did with our decimal, we take 4 plus 0 plus 1 equals 5. So, in decimal, so this number in binary is the equivalent to 5 in decimal. And that's how binary works. Suppose I could speed this part up. Alright. So, if you realize that say you have a longer number, like, I don't know, 1, 1, 1, 1, 1, 1, 1, 1. That's a binary number, guys. So if we think about each of these place values as just being powers of 2, well, let's work through that real quick. So this will be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. Let's work through those real quick. So 2 to the power of 0, anything to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 times 2 is 4 times 2 equals 8, 2 to the power of 4 equals 16. But basically, if you notice there's a pattern here. So we're going down in decimal, each of these numbers doubles basically. 32, 64, 128. Might notice there's some similarities between like our SD cards and our USB drives. We have like 64 gigabytes, 128 gigabytes, 16 gigabytes. There's a reason for that. Anyway, yeah, binary is pretty simple. You just, whatever one you happen to have, you take that number. So in this case, we have all ones here. So if we add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 should equal 255. Well, I was talking about these robot types. In the robot world and in Arduino too, this applies to Arduino, we have what we call a byte variable. Well, in Arduino and these robots, typically in most languages, a byte equals 8 bits. And this is our 8 bits right here. There is a finite limit to what a byte variable can hold in it. So if you declare like an Arduino byte X, and you're trying to keep track of how many times your program run or something, there's a finite limit to how big that number can get. And that is 255, because with a byte, we only have 8 bits to work with. 255 is the maximum amount that we can count to with a byte variable. Clear as mud? Anyway, you should see the looks that people give me when we're doing robot classes and I go through all these shenanigans. They're like, I did not sign up to learn computer science today. Thank you, mister. Go home. I think that's about all I had to talk about. I mean, we'll talk. Actually, that's not. We'll add a few things in real quick. So that was a byte variable. A byte holds 8 bits, and 8 bits can only store up to 255. And if you didn't know why, that's the reason why. Oh man, my table's getting more and more blue. Alright, so let's look at some of the other variable types real quick. So we just talked about the byte variable type. And in the robots, we have an int variable type and Arduino 2. And we have double variable types, and we have float variable types. There are some other ones, but these are some of the main ones. So we talked about the byte variable type and having a limit up to 255. Well, what happens when we want to keep track of a number that could have both a positive or a negative value? Well, that would be something we'd use an int variable type for. So a byte holds 8 bits. Well, an int will hold 2 bytes. So that's 16 bits, and if we go through our math and we calculate whatever 16 bits are, you'll find it goes up to like 64,000 something, which gives us a much bigger range of numbers that we could potentially store in this int variable. Integers use something that we call 2's complement to store both positive and negative numbers. And let's say we'll just make our 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 16 bits. Basically, the 2's complement, we're not going to go into a lot, but it looks at this first digit to decide what sign to give our number. So it'll change that first digit based on whether we're storing a positive or negative number. But there's a whole link on like Arduino. Put the link up there if you're curious about 2's complement and how that all works. But that's a little bit beyond what I wanted to go into today. But essentially what that does, in order to store both positive and negative, that 64,000 range or whatever that I just mentioned, it splits it in half. So our integer can store up to, I think, pretty sure I know this one, 32,767, and it can go down to negative 32,768. Yeah, so an integer variable, if we wanted to store a positive or negative value or something that could change from positive to negative in whatever we're doing in our program, we would store that in an integer variable. Sweet. But also in these integers, as far as Arduino stuff, applies to the Atmel boards. Some of the different boards like the Do and the Arduino Zero, stuff that's not based on the Atmel chip, they might not be 2 bytes. They could be like 4 bytes, or they work a little differently. So just make sure that you're aware of that if you're messing with different types of Arduino board. Arduino. The doubles, again, all this is kind of going through our variable types and being aware of what variable types we're using and that it matters, kind of be aware of what types of numbers you're trying to store in your program and what variable type should be used for the range that you're expecting that variable to hold. Anyway, doubles, we'll talk about doubles real quick. So these robots that I work with, essentially the robots, in order to know like where it is in space, each of the motors, like the bottom one that twists, all the motors that are on the robot have encoders on the back of the motors. What an encoder is basically a disc, and it shines a light through it, and it keeps track of how many pulses of light shine through that little disc as the motors are turning. And the amount of pulses between like a full rotation of the motor is really big. It's like 300,000 or 400,000 on these particular robots. Well, a number that's both plus and minus, because the motor can go both ways. With that kind of range, an int's not quite big enough. So we need to use a double on these robots to store our position data, which goes up to 4 bytes in this case, which can store like, I don't know, 4 billion. A number that goes plus or minus like 4 billion or something. I'm not positive. I'll have to like put a little linkers, do some post-processing in the video. But yeah, so in this case, like robots, each of the axis has to store really, really big positive and negative numbers. So for each of these motors, it stores the pulse data of each motor in a double. And just a little fun detail, we also have position variables in robots. And these position variables are an array of double variables. So on this case, we have 6 motors from top to bottom on a robot arm, and each of those 6 motors has to store like a snapshot of where that motor is for where that robot is in space, basically. So every time you're teaching a point with a robot, you're taking a snapshot of 6 doubles to take a screenshot of where your robot is in space, in any case. But it's an array of doubles. It's a little bit more detail than I intended to get into about this, but yeah. Doubles are it's the same as an int basically, except in Arduino, doubles don't work the same as an int in Arduino. Doubles actually store a floating point number in Arduino. So be aware of that. And basically in Arduino, at least on the Atmel boards, there's no difference between a double and a float. But in most other languages and robots in particular, a float, man, I'm getting messy. A float is what you use to store like a decimal number. Say we had 2.5 or 5.5 or something like that we needed to store. For instance, in the robot, I talked about the pulse counts on a robot. Well, that's one position system. Like we can also have an XYZ where we have like an origin point somewhere in the robot cell or wherever the robot's mounted, and we can keep track of an X, Y, I think, let's say X, Y, and then up and down a Z, and we can keep that in a decimal position value, wherever. That's another way to keep track of where the robot is in space, as we have just like an XYZ grid, if you remember that from high school, and then Z would be coming vertically in and out of the table like this. Yeah, capiche? Anyway, yeah, that's what we would use a float for anytime we need to store a decimal value. But I think that covers everything I wanted to talk about. Like, we talked about binary, kind of how binary works and why it matters what type of variable that we're using in our Arduino sketch or other programming, whatever, if you're using Python or any number of the other several hundred languages that are out there for programming, including robots. But yeah, guys, just be aware of what variable type you're using and what values that you're trying to store in that variable. That was the mistake I made with that Ant LED video. It wasn't really a mistake. Like, I was only using 10 milliseconds, which would be fine to store in a byte variable or a uint 8 variable like I was using. That's the same thing in an Arduino, a uint 8 variable. Well, if I were going to be putting like a 2-second delay in there, I'd have to store a value of 2000 in milliseconds, which is too big for a byte to store in there. So that's why I changed it to a uint16 variable type at the end of that video, in case you were wondering. Alright guys, this is Life Me Lightning, bringing some computer science into your life, I guess. Lightning bolts. I need a jolt. Lightning. Kapew!